of TR infinity, it's when you have a totally real ground field in an infinite place that splits completely. Then Stark's conjecture itself gives you that unit because it gives you the absolute value of a real number, which pretty much gives you the real number. In the case ATR, when you have a ground field that has exactly one complex place automatically splits completely. And Matt described a method using Shintani's method to give a exact formula for the log of the unit rather than the log of its absolute value. Now that formula wasn't entirely general. It was for just the cubic case, and there were some error terms and whatnot, and that is probably a reflection that of how things could be improved if they were smoothed. So that's something that's still open a little bit. So today I want to concentrate on the last case where you have a totally real field and the place that splits completely is a finite prime. So we're going to start by defining the Eisenstein series we have in mind. So we fix a weight k greater than 2, and we fix a pair of rational numbers v1 and v2. And the construction I'm going to define only depends on what they are up to addition by integers, so I might as well consider them in the quotient by z squared. And I'll take a z in the upper half plane and define an Eisenstein series, which I'll call ekv, which is going to be a sum over all integers that are not simultaneously 0, which is what the prime means. You take out the ordered pair 0, 0, and you sum a function that I'll call e, which is simply an exponential divided by mz plus n to the k. So here e of x is e to the 2 pi I x. Okay, so now this series converges absolutely because I've assumed that k is greater than 2, and so it's easy to check just by plugging into the formula and doing a change of variables that if you do the weight k slash operation with a matrix in SL2Z, so how's this defined? The weight k slash operation would be c to the negative k times the original function evaluated at az plus b over cz plus d, where gamma is a, b, c, d. Then it's easy to check just by plugging into the formula. You don't have to worry too much about how you're ordering the terms in the sum because it converges absolutely for these k's. Then it's easy to check that this has this property where this is just the natural action on a column vector. You think of this v as a column vector. Okay, so in particular, this ek v of z is a modular form. Okay, so it's a modular form on gamma of n. So matrices that are congruent to the identity modulo n, and where n is equal to a common denominator of v1 and v2, because then gamma times v is equivalent to v mod z squared, and therefore just by applying the fact that these are equal, I'm saying that it's invariant under the weight k slash operation of gamma. Okay, so that's a bit of notation for the Eisenstein series. Now, I want to introduce a little bit more notation, and I think this is consistent with what Glenn had in his lectures, which I'm going to let P sub k be the space of homogeneous polynomials of degree k, sitting inside, I'll say with complex coefficients for now, and if I want to consider all of them, so the direct sum of all the pk's will just be p. Okay, so maybe I shouldn't say that that's defined to be p. I think you know what the left side is. I should say that's p is defined to be that. Okay. Okay, and if I want to consider rational ones, I'll just call that p sub q. That'll just be okay. Now there's a weight. There's a natural action of gamma. So I don't think I said. Okay, so let me go back here for a moment. I didn't say where gamma was. I should have said this is for gamma in SL2Z. Maybe that was clear. This is for all gamma in SL2Z, and I'm going to call this gamma. So this is true for all gamma in SL2Z, and in particular if my gamma is in gamma of, if my matrix gamma is in gamma of n, where n is the least common denominator, then gamma inverse of V is congruent to V, so it's actually invariant and you get a modular form. But in general, if you have a general matrix of SL2Z, it just permutes these various EKVs around for the various V. Okay. So now if I have gamma in SL2Z, I can define an action, and I'm not sure if this is the same. I think this is probably different than the convention that Rob had, but this is going to be P, this is a left action, and it's going to be P of xy multiplied on the right by gamma. Okay. So that's just a bit of notation. And so the motivation for why are we considering these Eisenstein series, that Stark's conjecture is about zeta functions, is that there's a link between the two, which I'll call Siegel's formula. This appears in paper of Siegel, which is for real quadratic fields. So remember, I'm considering the case TRP, so we have totally real fields. So the most interesting case, other than the first case after Q, is for real quadratic fields. And we're going to pick an ideal, which is going to be the conductor of an abelian extension. We'll call K be KF. This is the ray class field of conductor F, I should say, attached to the conductor F. Now I'm going to consider a set of primes. So usually we call this S, but when you're dealing with the TRP case, it's better to call it first think about R, which is basically S without your P. So it's the minimum set you need, the infinite primes, and all the primes dividing your conductor. Okay, so I'm not going to throw in the prime that later I want to split completely. I'll deal with that later. Let's deal with just this minimum set first. And we fix another ideal A, okay, that's relatively prime to F. Okay. Then I write A inverse F, this ideal, so this is of some fractional ideal of F, so it's free of rank 2 as a Z module, and I can take a basis for it, which I'll call omega 1, omega 2. Now there's some orientation issues that you should worry about, so to make everything precise and correct here, I'll just write them down. You fix a real embedding of F, and you want to orient this such that omega 2 is greater than 0 in that real embedding. Just by switching omega 1 and omega 2, you can guarantee this happens if it doesn't happen when you first write down omega 1, omega 2. Now, given this data, I'm going to define a P and a V that I'm going to then apply to this Eisenstein series situation. So the P that I'm going to take, I'm going to define P of xy. So here's my polynomial, is going to be the norm of A, that's some integer, times what I'll write as the norm from F over Q x1. Well, I said xy, so okay, x omega 1 plus y omega 2. So this is the norm form with respect to this basis. So it's just this times the same linear polynomial with omega 1 and omega 2 replaced by their conjugates. Okay, so this actually has integer coefficients, this polynomial. So maybe, but in the notation, I'll just say it has rational coefficients, and it has degree 2. Okay, so now what other data do I need? Well, I need, I'm going to give you a matrix gamma in SL2Z, and that'll just be the matrix for multiplication by an element, by an epsilon, with respect to this basis. So what is epsilon? So epsilon is a generator of what Matt called E of F. This is the group of totally positive units congruent to 1 mod F. Okay, and then the last piece of data I need, hopefully it'll fit on the slide, is we define a pair V, Q squared, by the formula that I just write 1 in terms of this basis. Okay, it's a basis, over Q, it's a basis for F. Okay. So this matrix, sorry, I'll say one more thing. This matrix is in SL2Z. Okay. And then I guess I have to tell you how I normalize which epsilon. There's two generators of a free abelian group of rank 1. So I could normalize it based using the same real embedding I chose to normalize omega 1 and omega 2 by the condition that it lies between 0 and 1. Okay, so there's a lot of data that I've collected associated to a real quadratic field. So associated to a real quadratic field and an F and an A, I made a choice, which is this basis of this ideal, and then I produced a bunch of data from that choice. Okay, and Siegel's theorem is that if you fix any tau in the upper half plane, then for an integer r greater than 1, we have the following formula for the zeta function. Okay, so A enters, so it's the Frobenius associated to A, so it's a certain element of the Galois group of K over F. The value at 1 minus R is the following expression. So there's some constant up front. And then it's an integral tau to gamma tau. This is the linear fractional transformation, okay, of P of Z1 times, so this is the P that I defined here, that P, times E2R comma V, and that's the V that I defined there, of Z dZ. Okay, so that's Siegel's formula. And so this doesn't depend on the choice of tau, turns out. And maybe I'll say something about that in a moment. But the idea is that this is, so these Eisenstein series know about the values of the zeta functions, and we want to know something more than just zeta functions. We want to get a formula for Stark units. So the idea is maybe they know about the Stark units. So let's see more generally what happens in the process of multiplying Eisenstein series by polynomials and integrating them. Not necessarily these particular ones, but more general ones. So if you define, so now just to make the notation better, I'll define q squared mod z squared. And I'll take out 0. The reason I'm taking out 0 is I didn't talk about what happens at k equals 2. So the Eisenstein series in weight 2 is okay. It doesn't converge absolutely, but it turns out you can define it as a holomorphic modular form as long as v is not in z squared. So from now on, I'm just going to take out z squared. I'm going to allow myself to plug in k equals 2. Okay, so when I say 0, I mean the coset of 0 in here, so all of z squared. Okay, so now I'm going to define more generally just by exactly what Siegel, the right hand of Siegel's formula. So define psi tau of gamma as a function from, takes a p and a v and spits out a complex number by, okay, so I'll define it on a homogeneous guy, so for p and p sub d. And then I'll extend by linearity to general p's by defining by exactly, I just copy this down, the formula on the right. Tau to gamma tau of p of z1. Okay, so this is by definition, this is psi tau of gamma of pv. Okay, so now I'm not taking these special p and v, so it's not necessarily true that it doesn't depend on the choice of tau. This will depend on the choice of tau. Okay, so but how does it depend? So we're going to define a certain module. So first we'll think of it as just an abelian group of functions from p cross v to c. Okay, and maybe we'll put some conditions so that are linear in the p variable, and they satisfy a certain distribution relation. And since it's not going to play that big a role in this talk, I don't want to get into it, but I'll just say there's a certain distribution relation in the v variable.
So
R is little d, I think. Let's see. what is, okay, so this is, sorry. Okay, what do I want? So this is the case when d is 2r minus 2. So what I should do is make everything with a d. So this will be d plus 1 factorial. Yeah, so I just thought I could copy it, but I wanted to change a little bit. This is d plus 2, and this is d plus 2. Thank you. Sorry. So in this case, r is 2r, d is 2r minus 2. D is fixed, yeah, for a given p, and then you define it by linearity for general p. Okay. So yeah, you use a different Eisenstein series based on which homogeneous polynomial you take. Okay, so then this has a certain gamma action. So for f and m, okay, and gamma, we could define gamma f of PV to be f of gamma transpose P gamma inverse V. And I'll explain why there's this funny transpose. So if it's going to, it's a left action, and so if you work out left-right actions, it has to be either gamma transpose or gamma inverse there to make it a proper action. So which one do you take? It's going to be the one that makes the next proposition true. Okay. So all I've done so far is I've taken Siegel's formula and said, well, let's not plug in these particular P's and V's. Let's plug in general P's and V's and see what we get. And that's all I've defined so far. Okay, so then the proposition is that the property that this has is that psi tau of AB, if you calculate it, is equal to psi tau of A plus A psi tau of B. Okay, so for A, B, and gamma. Okay, and that's a little calculation you can do. That's pretty simple. And this is explains why we need this definition. This is the definition you need to make this proposition true. So what is this? This is exactly the cocycle property. So in other words, psi tau is a 1 cocycle for gamma acting on this module n. And furthermore, you can check that the cohomology class doesn't depend on the choice of tau. That you picked to define it. Okay. Now we're going to see what happens if we take this construction and we smooth it. Okay, so we're going to fix a prime L. Okay, and why are we smoothing? We're smoothing for 2 reasons. One, so this H1 is exactly the type of H1 that Pollock described in his lectures. Okay, he described his modular symbols could actually be mapped to an H1, and we're trying to do it with an Eisenstein series instead of a cusp form. So it's very much parallel to what Rob was doing. But the problem is that Rob was able to integrate from a cusp to another cusp because he was dealing with a cusp form. I have Eisenstein series, which blow up when you get to the cusp, so you can't integrate them. So one thing that smoothing allows you to do is actually integrate between cusps. So that'll be one thing we get out of the smoothing. Another thing it'll get is we'll be able to evaluate it exactly and get explicit formulas for it. And the third thing, and maybe the most important thing that it does, is that well, I didn't mention that Siegel was able to use this formula to give another proof of his rationality theorem, that these values are actually rational. He proved that these are rational. That if you smooth, you can actually get values that are integral. Okay, so there's 3 things that this smoothing does for us. So that's why we're going to embark on this process. So let's now define a smooth version, EK, which I'll call EKVL, which is L to the K minus 2. This is just some constant that makes things a little bit nicer. And I take EK of LV1, V2. So I'm writing V as a pair V1, V2, okay, of LZ minus EKV. Okay, so this looks a little bit complicated, but this is just the action of the matrix L0, 0, 1. And a property that's important that I didn't mention about the Eisenstein series is that it has a Q expansion, and the constant term of its Q expansion only depends on V2, it turns out. Okay, if you work out what the Q expansion is. So when I take this difference, the constant term cancels. The constant term is 0 because the V2s are the same. This is V1, V2, this is LV1, V2, so the constant terms cancel. This LZ doesn't affect the constant term. Okay, so this constant term is 0. Okay, so that's an important property that I'll exploit in a moment. But let me tell you something about what the smoothing has. So the property is, so now what about the weight K slash operator? Well, I want to say, is this equal to EK gamma inverse V sub L, like I had with my unsmoothed guys, my original guys, and this is still true if gamma is in gamma naught of L. So as long as your matrix is upper triangular mod L, then it still holds. And now you got to be careful about your V's because I didn't want V and Z squared, at least when K was 2. So now what I'm going to define is I'm going to only take in this equation V to be in what I'll call V sub L, which is what you need to do to make sure that neither of these is in Z squared. So I'm going to take out 1 over LZ plus Z, and then I'm going to mod out by Z squared. Okay? So I'm taking out a little bit more than 0. You can, well, okay, let me get into that. So, and then finally I'll define the smooth cocycle psi tau L of gamma of PV is the same as psi tau, but with the smooth Eisenstein series instead of the EKVs. Okay, so it's just this integral, this integral, which is fortunately written a little messily, but with a superscript L there. Okay? And the smoothed guy, the smoothed psi tau L of gamma, I shouldn't say of gamma, just the psi tau L, okay, is actually a 1 cocycle for gamma naught of L valued in ML, and of course what is ML? ML is the same as M, but with V replaced by VL. Okay, so now as I mentioned, the constant term of E K V superscript L is 0. So at infinity, okay, that was the Q expansion argument I gave, and then in fact, and at every gamma naught of L equivalent cusp as well, okay, that follows from infinity because of this property, here that I mentioned, that so if I slash by a matrix in gamma naught of L, so I move to a different cusp, then I just get a different EK for a different V, and therefore if it has constant term 0, then this guy did at gamma naught of L infinity. So these are all the rational numbers with denominator divisible by L. Okay, so so this is a nice property because what it allows us to do, this implies that we can take tau equals infinity in our definition, i.e. that psi infinity L makes sense. Because I can always integrate from infinity to another cusp in gamma naught of L infinity because the constant terms are 0 at those cusps. Okay, so this is what's called a partial modular symbol. Because I don't have a full modular symbol on all of P1 of Q, types of modular symbols that Rob and Glenn were using, we only have it on this subset of cusps, the ones that are equivalent to infinity in gamma naught of L. Okay. Okay. So now I want to state one of the three things that I mentioned. Okay, so I already mentioned the fact that now you could get a modular symbol because we've smoothed, and I didn't mention the explicit formulas, but there are explicit formulas for this. Okay, so one of the group projects that the group is working on is actually writing down what the formula is explicitly for this psi infinity L. Okay, but let me now mention the integrality result, which is the third feature I mentioned. And I'll put it in quotes because there's actually this is not written down, but so it's kind of weird to say that attributing a theorem to someone when it's not really a theorem, but so Henri and I did something similar to this. It was slightly weaker than this, but it's along the same lines. So one of the things the group will hopefully figure out is to work this out. But the idea is that psi infinity L of PV actually is okay. So I've explained to you why these are anything other than complex numbers. These are just line integrals in the complex upper half plane. But not only are they rational, but these actually lie in z bracket 1 over L if P, first of all, P of course, their polynomial has to have coefficients in that ring. Okay, and there has to be certain compatibility between P and V. So V is a vector. Okay, so I can think of plugging it in to P, and you need to know that P, not just V, but all its translates by this lattice, that all those values are integral. This is something you can often check in practice. Okay, so that's the statement, that these values actually have this integrality property. They're L units. Okay, and a little more precise, you can say a little bit more precise when this polynomial is just 1, the constant, which means you're integrating weight 2 Eisenstein series. So psi infinity of 1 in V actually is an integer. Okay, so this condition is automatic. This is just the constant 1. So if L, and this is L is greater than 5. If L is 2, you can get 4s in the denominator. If L is 3, you can get 2s in the denominator, or 3s in the denominator. Okay, so this is maybe not quite a theorem, but it's true. I think. Yeah, maybe we'll see if it's a theorem tomorrow. Okay. So now I want to go back to Siegel's theorem now that we have done the smoothing. Okay, so now we need to throw in some extra data now. So we're going to fix an ideal of a real quadratic field, C, in OF. So this is going to be a prime ideal, okay, so whose norm is L. Okay, so this might not exist. This is basically saying that L splits in my real quadratic field, or is ramified. Totally ramified. That was an inside joke to some of you. Okay. So tau is going to be the set C, prime ideal C, and we're going to pick our basis. So the only, sorry, T, that's not a tau, that's a T. So this is the set T that shows up in Stark's conjecture when you do the smoothing. So the smoothing on the Eisenstein series side is now going to show up on the zeta function side, the smoothing that I described in the very first lecture. And we have to choose a basis for the ideal. Okay, so we chose this basis last time, but we have to now choose it compatibly with this C, such that this this fractional ideal that contains it with index L has a basis 1 over L omega 1, omega 2. Okay, and then if you just use Siegel's theorem, then you see that that the L-smooth Eisenstein series, what that is giving you is just the T-smooth zeta function. So this is actually a simple calculation if you take for granted Siegel's theorem. It's just applying Siegel's theorem twice and taking a difference. That this is going to be psi infinity L. Well, it doesn't actually matter if it's infinity. It'll be true for any tau. V. But the corollary that so this is something that you get. But the corollary that you get from the theorem is that this value actually lies in. So this is just an easy computation using Siegel's theorem. But the corollary of the theorem is that this is in Z bracket 1 over L, because it turns out you can show that P and V have these desired properties that you want. Okay, and it's in Z if R equals 1 and L is greater than or equal to 5. Okay, so this is the theorem. This theorem, I think, was originally proved by Coates and Sinnett in the context. Two T's, yeah. So so this is a well-known theorem in the general setting of Deligne, Rivet, Kasunogos, and Barsky, but it was actually proved first in the real quadratic setting by Coates and Sinnett. Okay. Oops, this goes here. I mean, this was not their proof, but this is so. This is we're recovering the result. Okay. So so now what I want to do is move on to so we're actually very close now to being able to give a formula for Stark units using this co-cycle I defined psi. But I don't want to give it to you. I want to make you wait a little longer. And instead, I'm going to give you a completely different construction of another Eisenstein co-cycle, okay? Which should be related to this one, and that's one of the topics of the group project. Okay, so in the spirit of this conference, I think the best way to introduce this is by giving a bogus calculation. Okay, so what we're going to do is we're going to start with Siegel's co-cycle. So psi tau of gamma of 1v. So I'm going to just, for simplicity, take my polynomial p to be 1, the constant 1. So this is the weight 2k. So if you remember what the definition is, it's 2 pi I squared times the integral from tau to gamma tau of the sum as mn and z prime, so m and n are not both 0, of e of mv1 plus nv2 over m z plus n squared dz. Now again, there's convergence issues with this sum. You have to talk about what it means when n is when the weight is 2. But since this is bogus anyways, we're going to completely ignore that. Okay, so now, I mean, even this you should even take with a grain of salt, because you have to say what you mean by this. Okay, but especially what I'm going to do now is just crazy. So we're going to switch the order of in this non-absolutely convergent sum. We're just going to switch the order of summation and integration. So okay, so there's this factor 1 over 2 pi I squared. So I'm going to sum over mn and z prime e of mv1 plus nv2 and integrate from, so I can pull this out, it doesn't depend on z, so I get 1 over mz plus n squared dz. And now this is just some really easy integral to calculate, just 1 over a quadratic polynomial in z. So I can evaluate that. And it turns out, if you evaluate that this is equal to gamma tau minus tau over m times gamma tau plus n times m times tau plus n. Okay, so you could try to write, so you've gotten rid of the integral. Now I've gotten just a sum over m and z of this constant times this constant, okay? So there's no more integrals. But so Czech wants to write down a rational representative for this cocycle. He wants to do what we did, which is take a cusp for my tau. So he said, since this is all bogus anyways, we're not worrying about convergence. The reason we didn't take cusp before was because of convergence, but now we're no longer doing math, so we might as well just formally plug in tau, which is just a rational number, into the sum and see what happens to the sum. So you formally plug in this. Okay, so that's and what do you get? Well, you get the following. I'm going to write it in the sort of a nicer way. I mean, I could put it in and write this complicated formula in terms of R and S, but I'll introduce some notation which makes the formula a little nicer, which is I'm going to let sigma 1 be the column vector RS. So assume RS, of course, are reduced. And I'm going to let sigma 2 be gamma times the column vector RS. And I'm going to let sigma be the matrix whose columns are sigma 1 and sigma 2. So this is in M2 of Z. So it might not have determinant 1 anymore. It's just some integer matrix. Okay. So then psi of gamma of 1V. Okay. So what Czech wants to define now, so for Czech's cocycle, I think I'm going to call it a phi. So what Czech wants to define now is, okay, we'll put in this constant 1 over 2 pi I squared. Okay, so Czech will sum the same sum over all m in, so I'll write that pair as Z. Okay, prime. He's going to sum, so just what you get when you formally plug in RS into this expression. Okay, so this numerator turns out to be basically the determinant of this matrix sigma, which is why I introduced it. And the denominator is basically Z interproducted with this Z is just this pair Mn, interproducted with sigma 1 times Z interproducted with sigma 2, and then I need my E term, which is just now can be written as Z interproducted with V. Okay, so that's the definition that Czech wants to take of a cocycle. Okay, now there are two problems with this. So one is, what if the denominator is 0? And the second problem is, what about convergence? Okay, so you can always make whatever definition you want, so it doesn't matter if this was a bogus argument. If this made sense, I could still define it, right? But it doesn't make sense, because the denominator can be 0. Sigma 1 and sigma 2 are some vectors. There's going to be plenty of vectors in Z squared that are orthogonal to them. Okay, like negative SR will be orthogonal to R. So I have to say what to do with that. And then convergence, this still doesn't converge absolutely, so you have to say what you mean by summing it. Okay, so let's see. Okay, so I'm going to make an executive decision here, which is that based on what I have left, I think it would be in everyone's best interest if we stop now and then I just finish my talk. I go with Glenn and do an overflow, but my overflow will be something like 20 or 25 minutes, and then we can continue after lunch. So I'll stop here, and let me just outline what I'm going to do. I'm going to address these problems, and I'm going to define Czech's cocycle in general, and then I'm going to state an exact formula for Stark's conjecture using this construction. Okay.